or stored in an object?
Uh, Close. Basically, heat capacity or specific heat capacity deals with the amount of energy required energy needed to change temperature by 1 degree centigrade, right? So similarly, if I change the definition to specific heat capacity, it would become amount of energy required. It's always about the energy needed to change temperature by 1 degree centigrade of 1 kg mass. So in physics, if we add the word specific with any heading or any definition, the idea would be 1 kg of mass. So the difference between heat capacity and specific heat capacity is only about the mass. The main thing that we generally discuss in physics is always going to be specific heat capacity. Most of the times it's specific heat capacity, but sometimes the question will be about heat capacity as well, right? So the unit of heat capacity would be joules per degree centigrade. Simply put, from the definition, of course, energy for 1 degree temperature. So joules per degree centigrade. Over here, it's about mass as well, so this becomes joules per kg degree centigrade. And of course, since Kelvin is also one of the units, so this will also be found as joules per Kelvin. Similarly, this one also be found will be joules per kg Kelvin, right? One of the more uncommon units is also found as joules per grams. But since grams is not a standard unit, it's generally kilograms, we generally avoid this in our own calculations. But if the examiner gives us this as joules per grams, then we will be converting all the masses to grams. Okay. All right. Now let's try to understand what heat capacity or specific capacity would be in terms of real life. So it tells us simply, it only answers this one question: how much energy should I put in or should I take out if I want to change the temperature of XYZ object, that could be anything, by 1 degree? We are specifically looking for 1 degree, right? So if I analyze the unit of this, that is joules per kg degree centigrade. Okay, that means that if I write down, let's say, 4000 joules per kg degree centigrade, that means that for a mass or a block of 1 kg, let's say this is 1 kg, and if I want to heat it up or cool it down by 1 degree centigrade, the amount of energy that I need to spend or to extract out of it would be 4000 joules. So if I give in 4000 joules of energy, its temperature will rise by 1 degree centigrade. If I remove 4000 joules of energy, let's say, from this system, so it will lose 1 degree centigrade of temperature as long as the mass of the block stays 1 kg. Do we understand up to this point what this value means, right? Okay, so let's write down the formula for this. I'm working with specific heat capacity. Heat capacity is quite simple, but we can also always do the unit analysis and find out our answers. I will discuss unit analysis trick, that is basically from A levels, but if you try to understand it and implement it to O levels, it will help you to solve many questions that you are unable or you may be unable to solve if you forget their formulas. Okay, so the formula is Q equals to MC delta T. Just a moment. Okay. All right. So Q would be the amount of energy M would be the amount of mass, right? And C would be the unit of specific heat capacity. And yes, you're also right. To put it into simple words, that would be how much heat energy or how much thermal energy this object needs or can store over the passage of time if it has a certain mass xyz, or if it has a certain for the respective change of temperature. So delta T would be change in temperature, right? So always remember, this is energy. This is what we're trying to find out. And if you go back to the lessons that we've done before, energy will be treated as, you can say, simply put, it is treated as money, or you can say in terms of exchange, it is referred to as how much effort or how much work you may have done on this system and what did you get back. So energy is basically thought as simple, or you can say for a layman, it would be simply thought as the currency that enables you to do something or enables a machine to do something for you. Okay, so we look at it in terms of currency. So when I look at 4000 joules or these values, I just think about this as in this way, that I need to spend 4000 joules of energy so that 1 degree temperature can increase, or I need to extract or take out 4000 joules of energy to reduce its temperature by 1 degrees. Do we understand this idea? Do we understand the formula that all three are being multiplied, right? So mass will be in kg, specific heat capacity will be in joules per kg degree centigrade, and change in temperature will be in degree centigrade, although in some questions or sometimes you may find this in Kelvin as well. Theta is energy which is found in joules. Now let's do the unit analysis. This technique is from A levels. This will help you to solve many questions. It's not compulsory, it's not in religious syllabus, it's just your choice. You want to remember this, you want to keep this in your mind, totally up to you. You don't want to learn this, you don't want to keep this in your mind, it's up to you. It's not compulsory. So sometimes for these questions or any question in physics, you may get confused by the values given to you, right? So let's try to figure out how this formula and why this is equal to energy. Okay, so I just simply replace the units of all the quantities in the formula and see what happens. So this is joules per kg degree centigrade, and temperature is also in degree centigrade. So what I've done is simply replace all the units with the respective places, right? And what I see is that after being multiplied, I can see that kg is going to be cancelled with kg, and degree centigrade cancels out degree centigrade. So what am I left with? I'm left with joules only. So that tells me that this Q I believe that you heard up to this point, yes? That Q is equal to J?
Yes, it's just basic math.
Yeah, yeah.
The rest can cancel out just joules.
Yeah, yeah. So no matter the situation, no matter what question is given to you, you can still find out the final unit, and you can also manipulate the units in such a way to find out your respective quantity. Anyways, when we will solve the questions, we will also come back to this idea again. It's just your choice, nothing special, nothing compulsory about this. Now let's try to solve a question, that question 1. How much energy is needed to raise temperature of water of 5 kg from 20 degrees centigrade to 60 degrees centigrade? Now I can immediately see that this is a question for specific heat capacity, and he tells you that the specific heat capacity for water is 4200 joules per kg degree centigrade, right? So since the energy is my final outcome, is my final product, So I will simply write down the equation Q equals to mc delta T. This is what I need to find out in the question. So mass is given to me as 5 kg. So I'm simply write this down as 5C. Specific heat capacity is 4200. And delta T. Now we have to be careful about this. It increases or rises from 20 to 60. So my final temperature is 60 minus initial temperature, that is 20. Okay, so this is the approach of student 1. Another student, student 2, may have written this down directly as 5 into 4200 into 40. Both students will be considered correct, but I generally recommend to write it down as full form. Why? Because when you're going to recheck your paper, when the examiner is going to take a look on your examination and on your working, he will know that you knew how to calculate the value of 40. It leaves a good impression, and eventually your paper may be selected for a distinction as well, right? So I would prefer this method, that you put in full values and then write down your answer directly. Doesn't matter. So this is what we want to find out. Q is of our interest, so Q is the energy. We can find this by calculator now. So 5 into 4200 multiplied by 40, so we get 840 100,000, right, joules. I can simply write this down as 840 kilojoules. So I'm going to take a pause at this place, try to solve this question on your own once, and then we can move forward.
Yeah, you can give me another question, or
No,
basically the same
just
thing?
redo this one
Okay.
and verify the calculations.
Yeah, it's 840,000 or joules.
Right, so we
Eight.
so
Yeah,
you
that's it.
okay, all right. So this is a very simple understanding. The same question or same idea could be thought about for refrigeration, for cooling systems down. You see, how do they design the refrigerator is based on the same principle. What they do is they take the average heat capacity or specific heat capacity of all the vegetables, of all the food, or of all the material or substances that may be consumed by human beings, and eventually set a certain value or set a certain standard that, all right, if we want to cool down everything that is going to be placed in the fridge or the refrigerator, this is the amount of energy that is going to be provided to the refrigerator eventually, right, from the electrical supply. So one more thing let's add over here is that what if I wanted you to find out the power required to do this job? So the question would be extended in this way, that as part B or as a new question, that if this task was to be finished in, let's say, 5 minutes, right? So calculate power of the heater, right? So we understand that from the chapter of work, power and energy, the formula for power is energy, or simply work done by time. So what he has done, he has given me the values of time, right? I have time, that is 5 minutes. I have the energy that I need to spend or put in to this block of mass, that is 840,000 joules, right? So I replace energy as 840,000 divided by time, which is 5 minutes, but I need to convert this into seconds. And now I can find out the power of the electric heater. How powerful should it be in order for this system to work or to finish its job within a time frame of 5 minutes? So the value that I'm getting right now is 2800 watts. So you might have seen that when you go to the market to buy an air conditioner or a fridge or any equipment that eventually cools something or heats something up, they generally recommend or they generally talk about it in terms of watts, that this heater is 1500 watts, 2000 watts, XYZ, and so on, right? So what they're trying to tell you is how quickly that element or that equipment can achieve that task, right? Do we understand up to this point how the question may be extended, right? Okay, all right. Okay. Now, let's try to do a question for simple heat capacity. Now, in heat capacity, you won't find the value of mass. And even if there is, be careful about the value that he gives you for heat or specific heat capacity. That will eventually tell you whether the mass is relevant or not. So let's say that a block of mass 10 kg is given to you and you want to decrease its temperature from, let's say, 30 degrees to a temperature of minus 10 degrees, right? And the specific heat capacity is given to you as 5000 joules per kg degree centigrade, and the heat capacity is given to you as 7000 joules per degree centigrade. Now I know that my heat capacity has no kg in it, right? And my specific heat capacity does have a variable of kg in it, right? So even if the mass was given for this question and the value of specific heat capacity was missing, it doesn't matter, right? So the value or the final answer that we're going to get is can simply be found by Q is equal to C delta T. Now I'm going to use the same technique of unit analysis over here. I know that I want to find out the answer in joules, so what am I supposed to do with whatever variables that are given to me? Mass will be irrelevant, so what I can do is I can multiply or divide joules per degree centigrade with degree centigrade, so that degree centigrade gets cancelled out. I'm left with joules, which is eventually the unit of Q, which is what we want to find out for this specific situation, right? So this technique can be used if you forget the formula. You can just look at the units of the question and eventually cancel them out in such a way that it eventually becomes the formula. So we have 7000 as our joules per degree centigrade heat capacity, and change in temperature is from 30 to minus 10, which will be 40 degrees centigrade. Simply 30 minus minus 10, right? So this Q or energy can be found in this way. So 7000 multiplied by 40, that is 280,000 joules, or simply put 280 kilojoules, which would mean that you need to remove 280 kilojoules of energy from this system so that it eventually cools down from 30 to minus 10. So was the mass a part of the system? Was the mass used in calculation? No, because the unit or the heat capacity's value that was given to us doesn't have a mass in it. So this is how you will find, or you will look at a question of heat capacity. For a question of specific heat capacity, you will always find in its own unit joules per kg degree centigrade and a mass or a value of mass given in the question. Yes, do we understand up to this point?
Yeah.
All right. So this is the basic idea for heat capacity or specific heat capacity. We simply find the energy required to produce the change in temperature for a certain amount of mass. The next idea is latent heat. Latent heat. Now, latent in physics generally means hidden. In simple terms of English, it means hidden. So, latent heat, hidden heat, or hidden thermal energy. Why is it hidden? Why is it not visible to us? Is because we don't see a physical change taking place. Now, this is the amount of energy, simply energy needed to cause a change of state. Simple as that. So, from melting and boiling, when these processes are taking place, the amount of energy that we are putting in or extracting out of the system will be known as latent heat. But why do we say that it is hidden, or is not accounted for, or is not thought for directly? So when melting is taking place, we have a solid object being converted into a liquid, and when boiling is taking place, we have a liquid converting into a gas, right? So why is that so, that we call this latent heat or hidden heat? So basically, when we say that an object is melting, let's say we say that ice is melting, and we know that the melting point of ice is 0 degrees centigrade. It starts to turn from a solid to liquid when it reaches or hits the temperature of 0 degrees centigrade, right? So for example, let's look at the process. This is an ice cube that we already have. We start heating it up, and it eventually looks something like this, with some ice being solid and some ice turning into liquid, right? And eventually all of the ice becoming a puddle of liquid on the floor. Do we understand this idea? Yes? So throughout this process, from this point to this point, the temperature of the melting ice does not change. That is why it's called melting point, because it is happening at a specific temperature. Similarly, when we try to boil water, we call that as boiling point. We call that as boiling point of water, that is 100 degrees centigrade. So what's actually happening is that if you have liquid in a pan or in a pot, let's say, so you try to heat this up and it starts to boil, right? Unless all of that water that is in the pan, let's say, starts to boil, and eventually you have nothing left in the pan, for example, there is nothing left in the pan. So during this whole process, the temperature remains 100 degrees centigrade of the liquid, of course, right? That is why we call this a melting point. It's happening at a specific temperature. Even if you provide or keep providing it with energy, the temperature of the liquid will not change. So why physicists called this latent heat? Specifically for this reason, that we provide energy, but we don't see that translating into a change of temperature. So where is that energy going? That energy is basically used to break the bonds. So basically, latent heat was the energy used to break the bonds so that a change of state could take place. Do we understand this point?
Yeah.
Change of state takes place, right? So let's try to visualize this, what's actually happening. So we have these molecules of solid, for example. You provide it with energy, they start getting more agitated, and their vibrations, and let's say this is at 30 degrees centigrade. The vibration, and let's say that the melting point of this solid is 150 degrees centigrade. Let's say it's beeswax or wax or something that melts easily. So at 30 degrees centigrade, it's like this. At 100, the molecules may be more agitated, that their distances between them increases due to thermal expansion, right? This is the structure at 100 degrees centigrade. You keep on heating it, and you eventually reach 150. That is their melting point. At the current situation, they have the maximum kinetic energy, and they cannot vibrate any faster than this. They have reached their absolute limit of how strong or however strong their intermolecular bonds were. They are not good enough, or those bonds are not good enough to keep them together anymore. So exactly at 150, not even at 149, exactly at 150, these bonds, they are at their absolute limit. between the atoms. And of course, the bonds also exist in this direction as well, but I'm not drawing them to avoid any confusions right now, right? They're at their absolute limit, and if you keep on providing this energy, now this energy will not be used to increase the temperature, rather it will be used to break the bonds. So unless each and every single bond is not broken or is not taken care of, the temperature remains fixed. So basically, the scientists of that time could not account for this amount of energy that was still being injected into the system, but the temperature would remain the same. But one thing was changing at the time, and that was the state of the object. So it was melting, it was boiling, but the change of temperature could not be seen. That is why they named it latent heat. So I'm emphasizing this again and again so that it helps you remember that latent heat is the amount of energy that is only going to be used or is only going to be accounted for during the change of state, and no other time it is going to be discussed, right? So it goes both ways. Either it's for heating or either it's for cooling. Do we understand this point, that what latent heat is for?
Yeah.
Right?
So the reason it's called latent is you won't actually observe a change in temperature.
At melting point or boiling point, you will see a change in temperature if you add or extract the energy from the system. But if you are at the melting point or the boiling point, then you will not see a change in temperature. Rather, that energy that seemingly is disappearing into nothingness or seemingly is disappearing into nothing will be used or will actually be used to break the bonds for that specific scenario or for that specific element. That is why it looks to us that it's being hidden or it's being used, but we can't account for it. Do we understand this idea? Yes?
Yeah.
Right. So the formula end of this is very simple. That is simply Q equals to L for latent heat. This will be given to you directly, right? Or it is sometimes given to us as Q equals to ml. That is, again, since mass is involved, this will be called as specific latent heat. Do we understand this point? Right? So we will try to solve numericals of this concept, of this idea, in the next class. If you have any questions regarding what we have done today in terms of heat capacity, in terms of its numericals, in terms of its concept, you can ask freely.
No, I understood.
All right.
The